Assalamualaikum warahmatullahi taala wabarakatuh. My name is Rajesh Syamil Hakimi bin Rajadullah. My metric number AA190590. I am from section 3. Okay, now I will explain about BJT. Okay, BJT. BJT is a bipolar junction transistor, also called as BJT, is a type of transistor that use both electron and electron holes as charge carrier. A bipolar transistor allows a small current inject at one of its terminal to control a much larger current flowing between two other terminals, making the device capable of application of AND switching. Okay, for the structure, okay, this is the structure. Okay, BJT consists of three differently doped semiconductor region. First is emitter region, second base region, and third is collector region. These regions are respectively P-type, N-type, and P-type at PNP transistor, N-type, N-type, P-type, and N-type at NPN transistor. Each semiconductor region is connected to a terminal appropriately labeled as E for emitter, B for base, and C for collector. The base is physically located between the emitter and the collector and made from lightly doped high resistivity material. The collector surround the emitter region, making it almost impossible for the electron inject into the base region to escape without being collected, thus making the resulting value of alpha very close to unity and giving the transistor a large beta. A cross-section view of BJT indicates that the collector base junction has a much larger area than the emitter base junction. Okay, for NPN operation, N-type emitter region has a very high density of free electrons, while in a PNP transistor, the P-type emitter region has a very high density of holes. Current and electron flow backward, which may cause confusion. Since the base emitter junction is forward biased, free electrons from the emitter region easily cross the base emitter junction and go into the very thin lightly doped P-type base region. The P-type region is just lightly doped, which means that doesn't have many holes in it. In this case, only a small percentage of free electron from the emitter region can recombine with the hole in the base region. The small number of free electron from the emitter region recombine with the holes in the base region move through the base region of valence electrons. Okay, the free electron that enter the base region but did not recombine with holes move toward the reverse bias base collector junction. Since the collector region is connected to the positive side of the external bias voltage, the free electrons are attract to the positive side and swept across into the collector region. They exit the collector region and also move through the metallic collector lead into the circuit and return into the emitter region. Okay, next for PNP operation. Okay, PNP operation. The operation of inside PNP transistor is very similar to NPN type, but the roles of the transistor and hole are swapped. The external bias voltage and the current direction are all reversed. If you try to understand, okay, PNP transistor forward bias the base emitter junction of PNP transistor and reverse bias the base collector junction. Since the base emitter junction is forward bias, holes in the emitter region can move through the base emitter junction and enter the base region. At the same time, electrons in the base region can also move into the emitter region. Inside the PNP transistor, the emitter current is due to the movement of holes from the emitter to the base region, but externally, emitter current is due due to the movement electron from the emitter region to the positive terminal of the external bias voltage. The base current produced in a PNP transistor is due to the movement electrons from the external bias voltage into the base region. Since the base region is just slightly doped, only a small number of electrons in the base region recombine with the holes from the emitter region, and the rest of the holes move into collector region. Okay, next for configuration. For voltage gain at common base is high, for common collector is low, and common emitter is medium. Okay, for current gain, common base is low, for collector is high, and emitter is medium. For power gain, base is low, collector is medium, and emitter is high. Input or output phase relationship 0 degree, for collector is 0 degree, and emitter is 180 degree. Input resistance is at base is low, at collector is high, and common emitter is medium. Okay, next we go to datasheet. Okay, this datasheet I Google. For example, I take the 2N and 390. Okay, this is datasheet. Okay, this is the datasheet from the manufacturer. The manufacturer is Microelectronics. Okay lah. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shalim binti Amir Saifuddin, and my number matric is AA191472. Today I will present about JFET characteristic, which is introduction and overview of JFET, including of the structures, operation, and configuration types. Also discuss an available type of JFET in market based on the official and provided datasheet from any semiconductor manufacturer. The introduction of JFET. The JFET is stand for the junction gateway effect transistor. It can be utilized as switches or transistors that are electrically operated or implement and amplify using the JFET. In a JFET, the semiconductor material is also positively and negatively doped. It is control devices that no biasing current is needed. It is unipolar devices that only operate with one type of charge carrier. It is also very high input impedance, makes them very sensitive to input voltage signal and less sensitive to temperature variation. FETs are more static sensitive than BJT output changes when input changes. The construction of FETs are more easily and better suited for integrated on integrated circuit IC and occupy less area of what. FETs are built in smaller size, less noisy, the low power consumption, and relatively low power dissipation. Those will improve the overall circuit performance. JFET are often mentioned to as devices on depletion mode. Instead, they depend on the principle of the region of depletion, which is devoid of major charge carrier. To allow the current flow, the depletion region has to close. The structures of JFET. There are two general classes of FETs family, which are JFET and MOSFET. The JFETs are primarily known as N-channel and P-channel. Both are classified on the basis of the basic semiconductor material used at the time of manufacture. The N-channel is widely used in fabrication. The three terminals of JFET are drain, source, and gate. The drain terminal and source terminal are connected to the N channel. The gate is connected to the P-type material. The narrow bar of N-type semiconductor material is first taken for the manufacture of N-channel JFET, and then two P-type junctions are diffused on opposite sides of their middle section called the channel. All mid contact at their end are formed in the long channel of the semiconductor material to form the source and drain connection. One or both sides of N channel are formed a PN junction. The operation of JFET. Accumulation electrons at the negative pole of the drain source are the source. The electron deficiency or hole at the positive pole of the voltage applied is the drain, and the gate voltage is govern the width of the N channel and thus the flow of charges of source to drain. There are three basic operating conditions for a JFET N channel, which are VGS equal to 0, VDS increase to some positive value, VGS less than 0, so VDS at some positive value, and voltage control resistor. There are three states at VGS equal to 0, VDS increasing to positive value, A. VGS equal to 0, VDS increasing to some positive value, B. VGS equal to 0, VDS increasing to some positive value at pinch off, C. VGS equal to 0, VDS increasing to some positive value, saturation. The operations of JFET at VGS lower than 0, VDS at some positive value. As VGS becomes more negative, the depletion region increases. When ID lower than IDSS, the JFET experiences pinch off at a lower voltage VB. ID decreases, ID lower than IDSS. Even though VDS is increased, eventually ID reaches 0 ampere. VGS at this point is called VP or VGS off. At high levels of VDS, the JFET reaches a breakdown situation. ID increases uncontrollably if VDS larger than VDS max. The operations of JFET at voltage control resistor. The region to the left of the pinch-off point is called the off-mid region. The JFET can be used as a variable resistor where VGS controls the drain source resistance. As VGS becomes more negative, the resistance increases. The configurations of JFET. There are three basic bias circuits, which are the fixed bias, self-bias, and voltage divider bias. The general relationships that can be applied to the DC analysis of all FET amplifiers are ID nearly to 0 ampere and ID equal to IS. By applying the Shockley equation to relate the input and output quantity, which ID equal to IDSS in bracket power of 2 1 minus VGS over VP. The configuration of JFET for fixed bias configuration, it can be solved directly using either a mathematical or graphical approach. The coupling capacitors C1 and C2 are open circuit. By using KVL, those indicate loop result in negative VGG minus negative VGS equal to 0. So VGS equal to VGG. The resulting level of drain current ID is now controlled by the Shockley equation, which is ID equal to IDSS in bracket power of 2 1 minus VGS over VP. For the output section of the fixed bias configuration, by using KVL, VDS plus IDRD minus VDD equal to 0. So VDS equal to VDD minus IDRD. We know that Vs equal to 0 volt, so VDS equal to Vd minus Vs, so it will get Vd equal to VDS. For VGS equal to Vg minus Vs, by applying Vs equal to 0, the lastly the equation is VG equal to VGS. The configurations of JFET for JFET self-bias configuration. This type of configuration eliminates the needs for two DC supplies. The gate to source voltage is now controlled by the voltage across a resistor Rs. For the DC analysis, the capacitors can be replaced by open circuit and the resistance Rg replaced by a short circuit equivalent since Ig equal to 0 ampere. Since Is equal to Id, therefore VRS equal to IDRS. For the indicated closed loop, negative VGS minus VRS equal to 0. So negative VGS equal to VRS, hence VGS equal to negative IDRS. For the output circuit, VDS equal to VDD minus ID in bracket RS plus RD. So VS equal to IDRS. So we know VG equal to 0. Hence VD equal to VDS plus VS equal VD minus VRD. The configurations of JFET for JFET voltage divider biasing. A voltage divider biasing circuit has only one power supply. All capacitors are open circuit. Since the gate source is reverse bias, Ig equal to 0 ampere, thus IR1 equal to IR2. By using the voltage divider rule, the voltage VG and R Thevenin can be founded as follows. VG equal to R2 times VDD divided by R1 plus R2. And R Thevenin equal to R1 parallel to R2. For indicated loop, VG minus VGS minus IDRS equal to 0 or VGS equal to VG minus IDRS. The Q point of the voltage divider circuit can be determined by using graphical method. The steps are 1. Plot the line by identifying 2 points which VGS equal to VG, ID equal to 0 and VGS equal to 0, ID equal to VG divided by RS. Second, plot the transfer curve by plotting IDSS, VP and calculated values of ID by using Shockley equation. The Q point for the circuit is where the line intersections the transfer curve. Using the value of ID at Q point IDQ, solve the other variable in the voltage divider bias circuit is VDS equal to VDD minus ID in bracket RS plus RD. So VD equal to VDD minus IDRD and VS equal to IDRS. So it will give IR1 equal to IR2 equal to VDD over R1 plus R2. Other method in determining the Q point is by using mathematical approach. This is done by solving equation ID equal to IDSS in bracket power of 2, 1 minus VGS divided by VP and VGS equal to VG minus IDRS. Thus, it will give ID equal to IDSS in bracket power of 2, 1 minus VG minus IDRS over VP. This is overview about the datasheet of manufacturing JFET. This is a N-channel JFET for J201 to J204 or SST201 to SST204. The purpose of using this JFET in the market is to amplify a low gain signal to high gain with filtration of noise. Also, it can be used in audio preamplifiers, mic preamplifier, and related circuits. Moreover, it can be used in infrared signal detection and amplification. The application of using this JFET is for sensor circuit, audio preamplifier circuit, audio amplifier stages, laser detection and data amplifications, and lastly is for infrared detection and data amplification. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif Naim bin Rosman. my metric number is 19069. Today I will tell about the comparison of BJT and JFET. Okay, for the carrier, BJT is bipolar and JFET is unipolar. And for the symbol, you can see this at the diagram for BJT and JFET. And for device type, BJT used for current controller device and JFET used for voltage control device. And input independence for BJT is low and input independence for JFET is high. And for the gain, high gain for BJT and low medium gain for JFET. And next, power consumption. BJT consume more power and JFET it consume less power. And for noise level, BJT consume high noise level and JFET it consume low noise level. For the thermal sensitivity, BJT is low and JFET is high. And for the size is large and JFET is small. Application preference is it prefer in low current application and it prefer low voltage application. Okay, for the example of BJT is used in a timer for delay circuit and used in electronic devices such as LCD because it have a small size. That's all from me. Thank you.
Divided by integrate for JFET. So this circuit except from the final examination paper of electronics session 2020/2021. Okay, so in figure C1 shows a voltage divider by a JFET circuit. Find the input impedance Zin, output impedance Zo, and the output voltage Vo of the amplifier. If the input signal Vin equal to 2 mV and the AC output impedance Rd equal to infinity. So here, given that VDD equal to positive 16 volt, R1 equal to 2.1 mega ohm, R2 equal to 270 kilo ohm, Rd equal to 2.25 kilo ohm, Rs equal to 1.50 kilo ohm, VDS equal to 7 volt, IDSS equal to 8 milliampere, and VP equal to negative 4 volt. Okay, so the first one we need to find the value of Vg. So to find Vg, we need to use the formula R2 over R1 plus R2 times with Vg. So right here we can see that R2 is 270 kilo over with 2.1 mega plus 270 kilo times with 16. So right here we can get the answer for Vg is 1.82 volt. And the next one, to find the load line, we use the formula VGS equal to VG minus IDRS. So when VGS equal to 0, so then ID equal to VG over RS. Okay, so right here, Vg is 1.82 over with Rs, which is 1.50 kilo ohm. So we will get the answer is 1.2
1.21 milliamp. So the coordinate is 0, 1.21 milli. Okay, so the next one, when ID equal to 0, so then VGS equal to VG, which is we have got the value of VG is 1.82 volt. So the coordinate is 1.82 and 0. Okay, so for transfer curve, okay, to find the transfer curve, we need to use the Shockley equation, which is the Shockley equation is ID equal to IDSS in bracket 1 minus VGS over with VP square. So this is the Shockley equation. So when ID equal to 0, so then VGS equal to VP, which is VP is negative 4. So the coordinate is 0, negative 4. So then when VGS equal to 0, so then ID will be equal to IDSS, which is IDSS is 8 milliamp. So the coordinate is 8 milli and 0. And when ID equal to, so to find ID is IDSS over with 4. So we will get 8 milli over 4, we get 2 milliamp, and VGS equal to VP over 2. So VP is negative 4 over 2 will be negative 2 volt. So the coordinate right here is 2 milli and negative 2. Okay, so we need to do the graph. Okay, so here is the graph that I have sketched, which is right here. IDSS is 8 and the VP is negative 4. And okay, so right here is the Q point, which is IDQ is 2.4 milliamp and the VGSQ is negative 1.8 volt. And then the value of ID 1.2 milliamp and the value of VG right here is 1.8 volt. Okay, so when we have all the value, we can sketch the AC equivalent circuit. So the AC equivalent circuit for voltage divider of JFET is like this, which is right here we have Vn. And right here is the VGS, and right here we have the GNVGS, and then we have the RD, and right here is the VR. So from here we can see the Zin, and from here we can see the Zo. Okay, so the next one So to find the input impedance Zin, so Zin equal to R1 parallel to R2. So right here you can see that R1 is 2.1 mega and R2 is 270k. So 2.1 mega parallel to 270k. Okay, so 1 over 2.1 mega plus 1 over 270k. Okay, so right here we will get the answer is 239.24 kilo ohm. So this is the right thing. And for the output impedance, which is XO, so ZO equal to RD, which is right here. RD is 2.25 kilo ohm. Okay, so to find out, first we need to find the GM. So GM, the formula that we will use is 2IDSS over with in modulus VP in bracket 1 minus VGS over VP. Okay, so right here IDSS is 8 milli, VP is in modulus negative 4 times with 1 minus VGS is 1.8 over with VP, which is VP negative 4. So right here we will get 16 milli over 4 times with 1 minus 0.45. So 4 milli times with 0.55. So the answer for GM is 2.2 milli. So right here we can find the voltage gain, which is AV equal to VO over Vin. So negative GM RD. So right here negative, which is GM, we have that the value is 2.2 milli times with RD, which is RD is 2.25 kilo ohm. So we will get the answer is negative 4.95. And so the VO is VO equal to VI AV. So VI we get is 2 milli, which is have been given from the question, times with AV, which is negative 4.95. So we get V out is 9.9 millivolt. Okay, so right here we have got the value for Zin. So therefore Zin equal to 239.24 kilo ohm. Z out equal to 2.25 kilo ohm, and VO equal to 9.9 millivolt. So this is the answer for this question. Thank you. Okay, so now let's move on to the next question, which is this is the voltage circuit I get from the Dashad module. Okay, so in this question we need to find the value of RE, ZI, ZO and also the AV. Okay, so before we can find the value of RE, we need to find the value of IE. And to find the value of IE, we need to do DC biasing. Okay, so in DC biasing, first we need to find the RTH, which is the R Thevenin. Okay, so to find the R Thevenin, R1 parallel to R2. So right here we can see that R1 is right here and R2 is right here. So R1 is 56 kilo parallel to 8.2 kilo. So 1 over 156 kilo plus 1 over 8.2 kilo. So right here we will get the answer is 7.15 kilo ohm. So we have get the value of. Okay, so to find the value of RE, first we need to find the value of IE, and to find the value of IE we need to do the DC biasing. Okay, so to do the DC biasing, first we need to find the R Thevenin. So to find R Thevenin is R1 parallel to R2. So right here R1 is 56 kilo ohm and R2 is 8.2 kilo ohm. So R1 is 56 kilo parallel to 8.2 kilo. So 1 divided by 1 over 56 kilo plus 1 over 8.2 kilo. So right here we will get the answer is 7.15 kilo ohm. And for the V Thevenin is R2 times VCC over with R1 plus R2. Okay, so right here VCC is 22 volt. So R2 is 8.2 kilo times with 22 over with R1 is 56k plus with 8.2 kilo. Okay, so right here we will get the answer for V Thevenin is 2.81 volt. Okay, so when we have the R Thevenin and V Thevenin, we can find the value of IB. So to find IB equal to VTH minus VBE over with RTH plus beta plus 1 times with RE. Okay, so right here VTH is 2.81 minus with VBE is a fixed value which is 0.7 over with RTH is 7.15 kilo plus beta, right here beta is 90. So it's right here 90 plus 1 and times with RE. So the RE is 1.5 kilo ohm. 1.5 kilo. So IB we will get 14.69 microampere. And when we get IB, we can find IE. So IE equal to beta plus 1 by B. So beta is 90, 90 plus 1, and IB is 14.69 micro. So we will get the answer is 1.34 milliamp. So when we have get the value of IE, we can find RE. So the formula of RE is 26 millivolt over with IE. So right here 26 milli over with IE is 1.34 milli. So the value of RE is 19.45 ohm. So that was the value of RE. Okay, so before we moving on to find the value of ZI, ZO and AV, first we need to draw the AC equivalent circuit. So the circuit will be like this, which is right here. We will have the beta RE, and we have R1, RB, and right here is VE, and right here we have I1, and right here we have IB, and from here we will see that and then right here we have the beta IB, and then we have the RC, and right here we have V out. So from here we will see Z out. So in this equivalent circuit, we just ignore the RO with R0, which is the value is infinity, so we just can ignore it. Okay, so next we want to find the value of ZI. Okay, so to find the value of ZI, we can use the formula RTH parallel to beta RT. Okay, so RTH right here is 7.15 kilo parallel to the value of beta is 90 times with RE that we just calculate just now, which is 19.45 ohm. So we will get the value of ZI is 9.4 kilo ohm. And then to find the value of ZO is equal to RC, which is the value of RC is right here. This is RC, which is 6.8 kilo ohm. And the last one to find the value of AV, which is the voltage again, is negative RC over RE. So negative RC 2.8 kilo over with RE that we just get, which is voltage gain is negative 349.61. So therefore the value of RE equal to 19.45 ohm, and the value for ZI is 1.4 kilo ohm, ZO is 6.8 kilo ohm, and voltage gain AV is negative 349 and 6. So this is the final answer for this circuit.